Hey there, folks. Let's talk about a little bit of new stuff. We've got a bit of work to do on Tuesday already, but I thought I'd throw this in and let you take a look at these problems too if you're finished with the previous 5.1. We talked about in the last lecture. We talked about relations and some properties of relations, and spent some time in class actually talking about defining more clearly where everybody could kind of follow what we meant by certain types of relations. And so today I want to talk about, this is actually in 5.2, what are called equivalence relations. Okay, so let's go ahead and define that. A relation on a, and I need to call it some R, on a set A is called an equivalence relation if it is simultaneously reflexive. Okay, what we mean by that is A is related to A for all A in the set A. Okay. Symmetric. Okay, and remember what we mean by this. This means that if A is related to B, then B is related to A for all AB in the set A. And transitive. And that means that if A is related to B and B is related to C, then A is related to C. And this is, put it over here, for all A, B, C in the set A. Okay? So, and when it does that, it has a nice property, and I want to spend a little time showing you an example of an equivalence relation and show you kind of the property it has. Let's define a relation. It's called A congruent to B mod n. Congruence modulo n, and this is for, really, you can do AB real and n just non-zero. ABN all real and let n just be non-zero. But for my purposes here, I'm going to stick with integers. So A, B, and n. Wait, I got to leave n out of there. Integers. N is natural numbers minus the 0. Okay. All right. Excuse me. All right. So, and really, what this means, we're going to define this by saying, okay, this means that n divides A minus B. So A is congruent to B. Here's the way we say it. A is congruent to B mod n. Okay, there we go. A is congruent to B mod n if n divides A minus B. Okay? And in the case that we're dealing with, where A and B are integers and n is a non-zero positive number, this is basically equivalent to A and B have the same remainder when divided by n. And it's really not too terribly tough to see that. Here's kind of the I'll show you instead of prove it to you, but which is basically the same thing. But I'm just saying that, you know, if you take n, or I'm sorry, you take A and divide by n, then this is, you got some quotient of A times n plus, and then you got some remainder that goes with A, where the remainder is between 0 and n, can't be equal to n. And then B is Q sub B times n plus some RB. You know, there's some quotient there. We don't know what it is. But then R here is between 0 and n as well. Okay, if we start with this one and we say, okay, n divides AB, then that means, and I'm leaving out the English because I don't want to dwell on it, but this means that there exists some k that's an integer such that A minus B equals nk. But then if you substitute these things in there, then you get Q sub A times n plus RA minus, you got to streak the negative through this, Q sub B n minus RB, and this is nk. So let's think about, I can factor an n out a couple of these things, right? N, and there's QA minus QB, but then I'm left with R sub A minus RB. Well, n divides this and n divides that, so that forces then that n has to divide RA minus RB. But let's think about what those could be. Oops, and I put A there. That should be a B, right? So let's say I want to subtract that B. You run a negative through this, you get 0, you know, 0 times the negative is that. This turns around, you get a minus RB, and that turns around, you get a negative n. And let me stack it the other way. This would be a negative n less than a negative RB, which is less than or equal to 0. So then if you take into account here that you've got 0 less than or equal to RA, which is less than n, and you add these two right there, then you end up with, and I'm going to have to squeeze it in, you get a negative n, and this would now be a strict inequality, and this is RA minus RB. Now this is strict inequality in n. So what's the only number between negative Rn and positive Rn that we're guaranteed n divides? 0. So RA minus RB is 0, and that means RA equals RB. So it's the same deal. And actually it's even easier to go this other way, because if you assume they have the same remainder, what happens when you subtract right there? It's gone, so automatically this divides that. So it's pretty easy to show it both ways. But what I want to talk about, and what's so interesting about this relation between numbers, is what it does to the set Z. And so first thing I want to show you is that this is actually an equivalence relation. Okay, let me, I want to transfer pages here, but I'm going to put this back up here. I'm going to say A is congruent to B mod n, let's remember what that means. That means that n divides a minus b. Okay? Two things are related. Oh, sorry, divides. Whoop, there we go. Okay? So, let's consider modulo 4. Congruence. Congruence, is that the way to... Yeah, I guess it is. Okay, it doesn't look right. That's an N, that's why it's C. Congruence modulo 4. Oh, wait, I don't even want to... let's stick with N for just a second. Okay, all right. So let's consider... let's just kind of show that anything of that form is an equivalence relation. All right, let's consider reflexive. Okay. Let's look at, we want to show that A is congruent to itself, mod n. Okay, so let's consider A minus A. That's 0. And n divides 0. So A is congruent to A mod n. And that one checks out. Okay. Let's try symmetric. We assume that A is congruent to B mod n. Okay. Then that tells us that n divides A minus B. Okay. Then there exists some k integer such that A minus B equals n times k. But now multiply both sides by a negative. Then B minus A is n times a negative k. Actually, it's a negative nk, but then you pull that negative inside of there. Since a negative k is an integer, then, then n divides B minus A, and B is congruent to A mod n. Okay, so it's symmetric. And now let's consider transitive. Assume that A is congruent to B mod n, and B is congruent to C mod n. Well, then that means that n divides, let me get it right, A minus B, and n divides B minus C. But we actually showed, our sum theorem is okay well, sum theorem is the sum and one of the add-ins, but a pretty easy reach here is to say if it divides this and it divides that, then it has to divide the sum of those two things, right? Then n divides A minus B plus B minus C. Then n divides A minus C, and I think you see where we're going, and then A is congruent to C mod n, modulo n. Okay? Therefore, this is an equivalence relation. modulo n is an equivalence relation. Okay, so the question I hear pouring out of the internet at this moment is, oh, wow, good, so what? Well, okay, so let me show you kind of what this, how this would work and the kind of special properties they have. Let's consider congruence. I'm going to put a number with the n now. Congruence mod 4. Okay? And let's think about things that are congruent to 0. Oh, by the way, I meant to say this. Actually, if we just kind of think about this in terms of has the same remainder, well, certainly A has the same remainder as A when divided by n. If A and B have the same remainder, then B and A do. If A has the same remainder as B and same remainder as C, then A and C do. So, you know, it actually makes a lot of sense. Okay, remember what has to happen here. We have to have things that have the same remainder when divided by 4. So, if we're talking about things that are congruent to 0 mod 4, well, what other things have a remainder of 0? Well, things divisible by 4, right? So 4 would work here, right? Let's list some things that work here. 4, certainly a negative 4 would also work, right? Oh, it's congruent to itself, so I could put 0 in there. Maybe I shouldn't put the negative there. Maybe I should put it here and just list them in order. Okay. 8, right? And negative 8. And so on. All the multiples of 4. Okay. And when we're dealing with an equivalence relation and it's kind of set up what it is, we will sometimes use this notation. Okay, where we take one element out of the set and put square brackets around it and say, okay, this is all the things that are, this is the set of things that are congruent to 0 mod 4, and in this case, or whatever the relation is, okay? All right, let's think about 1. What things would be congruent to 1 mod 4? Well, I need things now that have a remainder of 1, or when I subtract, that difference is divisible by 4. Well, 5 would be an obvious choice, right? So let me start listing some of these things out. So 5, and certainly 1 goes in there, right? Everything's congruent mod 4 to itself. But also negative 3, right? Because the difference between 0 and a negative 3 is 4, okay? Or they have the same remainder there, okay? Because you'd have to have a one whole thing, one whole 4, and then to get a positive remainder, right? And then you got one thing left over. So basically this gets all the things starting with 1 and then multiples of 4. So 9 and 13 and on, and negative 7 and on and on and on. Okay? 2, let's think about this. Things that are congruent mod 4 to 2, well, has the same 2 divided by 4, it has a remainder of 2, right? Certainly 2 would go in this set, but also 6, right? 10, 14, could put 12 up here. And going the other way, negative 2, negative 6, and so on. And then, let's see, 3, well, mod 4, 7, right? Because the difference between them is divisible by 4. Or they each have a remainder of 3. Okay. Certainly 3 would go in this set, 7 would go in this set, and then 11, and then 15, and on and on. And if you're going this way, then -1 and -5 and on and on. So 1 and 2 and 3. And can you see that this is everything? Right? If I start thinking about 4, well, that's actually this. Right? And 5 would be this, and so on. And then that's one thing to notice. And then the other thing is that if you take the union of all these things, my doggy is barking something, I apologize. But if you take the union of all these things, I have no idea what he's barking at. 1, union, 2, union. These are called equivalence classes, okay? And you take the union of these equivalence classes, it gives you the entire set. Okay? So it's actually kind of cool what equivalence relations give us one way of partitioning a set. If we can find a relation that has those 3 properties, it gives us a cool way of partitioning that set, okay, into what are called equivalence classes. Okay? Alright, so I'm going to leave you with that bit of information and assign you 3 problems out of 5.2. In the next day or two, I probably don't have the time to do it tonight, but in the next day or two, I'm going to only give these problems out of 5.2, problems 4, 5, and 6. Okay, we'll do a bit more in some other sections about with equivalence relations, but this is just to get you started on them. Okay, it wouldn't be bad to maybe get those done if you can before Tuesday, because depending on how fast we spent a lot of time on those 4 properties last time, but now that I think folks are kind of getting them locked away, we'll probably move pretty quick on problems on Tuesday. So let's see if we can get through this stuff. Okay, that's it for now, and I will see you again next time.